Yeah, so if you go down to class notes, motion notes, get to this motion and position. Now, we talked about the importance of equilibrium in motion, right? And you saw with your force tables that if it was not in equilibrium, that the string was pulled in the direction that there was lacking equilibrium, right? There you had a heavier area on one end and a lighter on the other, and it went towards the heavier area, right? If it weren't for that little ring with the post in the middle of the table, it would have come flying off the table, right? Come flying off that pulley. Now, the reason for that is when you have an unbalanced system, right? An unbalanced system, meaning a lack of equilibrium, this leads to motion. Okay? Because that lack of balance, yes. This is, if you look at motion notes, it's about halfway down. You'll see it. Yeah. Okay. All right, so if you have the unbalanced system, what you're going to have is you're going to have motion because that system is trying to balance itself, right? So, for instance, when we walk, basically what we're doing when we walk is we're going to push ourselves over, and your walk is like a fall. You're falling. But then you catch yourself with your foot, and then you catch yourself with your foot again, and you keep unbalancing the system so that you move forward, right? That's why people who don't have muscular control with their legs and core area, abdominals, and lower back, can't walk because they don't have the muscular control to stop themselves from falling, right? So, look at people who have some form of paralysis, or like toddlers who aren't walking yet. That's all they do is fall down, right? Because they're trying to figure out how to catch themselves and how to balance and all that stuff. Now, we do it without even thinking about it because we've done it for so long. But that is a case of us unbalancing the system in order for motion to occur, right? When we push something, whenever we pull something, that's what we're doing, is we're unbalancing the system, right? And when that happens, motion is the result, right? And there's different ways that we're going to measure the motion, right? We're going to measure it through speed, through acceleration, both. But we have to make a couple of points clearer first. One is this idea of frame of reference, all right? Because if your frame of reference is going to determine how well and how you see the motion of the object. And this is why it's so important. That's what this little picture here is all about. In each of those cases, when those three people are moving, they're going to see a different situation, right? So if, in other words, too, if I'm walking here towards Liz, Liz sees my motion differently than what Emily sees, right?
Yeah.
Because what Liz's eyes are telling her brain is that there's an object coming towards her and it's getting bigger. And through all her life, she's figured out that when that happens, something is coming at her. Right? What does Emily see? That it's getting, and what's the object doing? Getting smaller, right? Okay. Now, it does get smaller in a different way, and kind of changing the angle that tells her that I'm moving at an angle rather than straight away from her. But these are very complex things that our brain does fairly easily, right? Our brains are pretty amazing that way, right? And that's a good thing, because if an object is flying towards Liz's head, she doesn't want to have to think and do all these calculations to see what the object's doing. She wants to be able to go like this and not get hit by the object. Right? And if she has to think it through, she's going to get hit by the object because it will take too long for her to do that. Right? That's a good system that we have to detect danger. Right? Now, she knows me and my smiley face, which is covered by that, my smiley eyes. She knows that I'm a friendly object, so probably not going to hurt her, so she doesn't worry then. Right? But if she doesn't, but if she's not familiar with it, then that will incite some fear. Okay? But the point is, and the psychology aside, that when we describe motion, how we are looking at the motion is important. Right? And that's where we start to talk about this distance versus displacement. All right. Now, I should say before we go to that, there's these three planes which you all are familiar with, hopefully from math class. Right? The XY plane, the YZ, and the XZ plane, basically the three dimensions. And sure, we're going to have motion along all three of those dimensions. But because, again, we don't have a lot of mathematics under our collective belts in here, we're really only going to look at one plane at a time, one dimension of movement at a time. Because once you start including other dimensions, that's when the math gets a lot more complicated. Right? And so I guess that's something for you all to look forward to later in your student careers. You can do that. But primarily, we're going to stick with one dimension. Right? But we're all going to look at up and down and back and forth a lot. Right? But we'll do it one at a time, usually. Okay, now, there's a difference between when we say distance that an object travels and displacement. All right? Now, distance is, it says if you have run a 50-meter dash, okay, it's a marker on track and field, shows how far you run. Now, when that is a distance. Now, when it says 50 meters, right, when you hear that, if you're running in the race, you're going to assume that that's on the track, right? But it might not be, right? It could be in a yard somewhere or in a field, right? But it doesn't say anything about whether it's going east to west, north to south, south to north, up or down. It could be 50 meters up a hill. Right? Now, typically, they're not going to do that because they want to have standard races. That would be harder. But when they say 50 meters, that's all they're worried about is what's the distance traveled. How far is it from point A to point B? All right. Now, that's different in displacement than displacement because displacement is the actual change in the position. So, for instance, if, again, and I'll just keep using Liz as an example, if I'm going to go talk to Liz, I could go from here to here and talk to Liz, right? Or I could start here and then I kind of come over here, talk to Emily, kind of go around and talk to these folks, and keep going around the room, keep increasing my distance traveled, right? And then I come over up here and I talk to Liz. Hi. Okay? So, in that case, the distance traveled is all the steps that I took around the room. You got to measure the exact distance for all the little paths I took there and ended up here. Okay? Now, displacement would just be from here to here. Okay? So, in both cases, whether I went from here straight to here or did that big path, the displacement would be the same. Because my change of position over that time period was the same. Right? Distance, though, was not. Now, the other thing that has to be kept in line here when we talk about distance when we talk about displacement, is direction. All right. Now, direction is which way is it going? All right. Because the displacement would be different if I go from here to here versus from here back to here. All right, those are opposite displacements. Okay, so again, this goes back to the frame of reference. The displacement will be based upon where I start and where I finish. Okay, so if Liz is looking at this, and the displacement will be the final position minus the initial position. Okay, now here's where the point of view matters, right? Because let's say this is, oh, I don't know, maybe 3 meters, or maybe 3 meters from Liz right here. Okay, so that would be my initial position, right? And then my final position would be about right here, which would be roughly speaking 1 meter. Okay? So, with that being said, what is going to be the displacement? -2, right? All right. Now, here is one of the big differences between distance and displacement. Distance is not going to have a negative sign because it's just how far do I travel. So distance would just be 2 meters. Okay? But then my displacement would be -2, right? Now let's say though that there was somebody sitting in that stool there. And they were doing the same measurement. Right? Would the displacement be positive or negative? Positive, right? Because the distance on the end, the final position, is going to be larger than the initial position. Because it's about the point of view. Right? So, and this comes to a major thing, and I've mentioned it in passing before. Remember, and this is definitely remember no matter what. You see a plus or a minus, that equals direction. And that's it. Okay? So, if somebody is looking at the person, right, or if we stay here with Liz, if I started here and ended up back here, then my displacement would be positive 2 meters. Right? Because I'm ending at a greater distance from Liz, but it's the same numbers. Got it? No? Right. I can't tell whether that's a yes or no.
Yeah.
Right? Because remember, it's final minus initial position. So if the final position is smaller, is closer to you than what the initial position is, you're going to have a negative displacement.
Yeah.
If it's farther away, the final position, you'll have a positive. So going away from you is positive, coming towards you is negative. Right? But again, it's relative. It's relative depending upon who is looking at the object. Right? What is the frame of reference? Okay. Any questions on that? Now, what difference does this make for our calculations? Well, that's what I'm going to tell you right now. When we are dealing with speed, speed is just distance divided by time. All right. So if I wanted to get the speed of my change in position here, my 2 meters changed, then I'd have to have Emily or Joey here take a stopwatch and start when I move here and then stop when I get here. Right? And then you can divide the 2 meters I moved by the time it comes up on that stopwatch for the number of seconds. Right? And that would be in meters per second. Easy enough, right? So speed is just distance divided by time. So if you're in a car, how do you tell how fast you're going?
The speedometer.
The speedometer, what are the units for that? Miles, distance, per hour, time. Got it? No big deal. So that's how we do speed. Distance divided by time. Typically speaking, it's going to be in meters per second, but it doesn't have to be. It can be miles per hour, it could be miles per second, kilometers per second, whatever, depending upon what the problem asks for. But probably 60, 70% of the time, it will be meters per second. That's just kind of the standard way that we do things. All right? So when we do speed, notice the word here. Distance. All right? We don't worry about, did it get farther away, did it get closer, whatever. Has nothing, when you talk about 60 miles an hour in your car, that says nothing about which direction you're going. Right? That may even be an average speed. You may be going on some back road somewhere. Hopefully not. A little faster you go on the back roads. Don't do that. But, so you could be going on curves and whatever in different directions, but you still have that same speed. Doesn't say anything about where it's going. Right? So, that is going to be the big difference between speed and velocity. Right? Okay. And then your velocity is going to be in a given direction. So this is using displacement. All right. Now, one last thing I want to hit before we look at the problem solving. We have two different types of speed and velocity. We have instantaneous and we have average. Okay. Now, especially looking at root words here, what do you think instantaneous means? Instant, right? So maybe when little Joey was in trouble, his mother would say, Joey, get over here this instant. What does she mean by that?
Get over there now.
Right now. This point in time, right now, specifically, this point in time. So that's what instantaneous velocity is. So maybe you have a car that's traveling in and out, going around curves, it slows down a little bit. So all the little points in time would be a bunch of instantaneous velocities, instantaneous speeds. Okay? So that's really what the speedometer in a car gives you is instantaneous speed. Because you kind of speed up and slow down, you can see it move. Or you can see, because digital readout, you'll see the numbers change. Because it's telling you how fast you're going at that specific instant in time. All right? So we'll say instantaneous is at a specific point in time. Whereas the average would be like what I gave with my example here. Have somebody start the timer, and then I start here and go 2 meters, and then they start and stop it. So, I may not go a consistent speed or that. I may slow down a little bit as I walk. Whatever, doesn't matter. How fast it takes me to get from point A to point B. Primarily, when we do our calculations, we're going to be looking at average speed, because average speed is more helpful than instantaneous, right? All the instantaneous values add up and average out to the average speed. And we'll say this speed, velocity, over, dang it, an interval of time. Okay, great. Now, I don't know why. Maybe you want to draw pictures there or something. I don't know why I left the big space, but whatever. We're going to go through how to solve some of these problems. I put a link out here to the side if you want to copy it from this. This is kind of a good page to give you some extra explanation on it to help you. All right. And I also put in this box right here. This box right here gives you a step-by-step setup, and I recommend you kind of going through that every time, making sure that you're hitting the steps. And you always want to do your problems systematically. Do them the same way every time so that you get good, consistent results. Now, let's take a look at this. We have Hans stands at the rim of the Grand Canyon and yodels down to the bottom. Okay? Kind of a fun sentence, right? Does that sentence mean anything? No, not really. Not for solving it. I mean, yeah, it's kind of fun to think about somebody yodeling down the Grand Canyon, but it doesn't really help us solve the problem. He said he hears his yodel echo back from the canyon floor. Here we go. 5.2 seconds later. Assume that the speed of sound in air is this. How deep is the canyon at this location? So, if we look back here at our formula for speed, all right, speed is distance divided by time. All right, so if we want to use then, we'll say d over t. Okay, so we did step one there, right? We read the problem carefully, figure out exactly what it's asking for, right? What is it asking for? Which of these variables? Is it asking for speed, distance, or time? Distance, right? Because it says how deep is a canyon. So that's a distance. So we want to solve for distance. As read problem again, write down all the information you're given, such as speed and distance. All right, that sounds like a good idea. So we have speed equals 340 meters per second. We have distance is we don't know, and time is 5.2 seconds. All right. Good. So now what we need to do is we're going to have to set up this problem. All right. It says write down the relationships or formulas that apply to either the answer or the information you are given. Okay. So again, out here, if speed is equal to distance divided by time, how can we solve for distance? Yeah, go ahead. Well, you can. What I'd rather you do is to do the relationship first. Algebraically, how are you going to isolate distance? Go ahead. Good. Multiply both sides by time, because then our time will cancel. So then time multiplied by speed is equal to distance. So then we are going to plug these things in. But wait a minute, let's think about this. So here's the yodel echo back from the canyon floor at 5.2, yeah. Ah, good. Right? Because if you're yodeling down the canyon and it takes that long for it to go down and come back, all you really care about is the time down, right? Because that's the distance down. So we're going to take half of 5.2 as our time. All right. So if somebody does the calculating, that would be good. What is it? What's 5 equals 2.6? All right. So we have 2.6 seconds times the speed of 340 meters per second is equal to our distance. Notice there, seconds will cancel. That's good because we're looking for distance, and distance is meters. So what is 2.6 times 340? What is it?
884.
884 equals our distance. Okay? Got it? Not too bad. A little bit of algebra magic, and we're in business. Don't worry if you're confused right now. We're going to be doing lots of these. Just keep paying attention and do all the problems along with me. Don't sit back and admire how lovely everything is when I'm doing it, because that's not going to help you, right? Getting your hand involved will get your brain involved. Okay? So, I know. Go ahead and look at the horse racing one and take a minute and see if you can solve that. By the way, do we have any runners here? So how far is 800 meters?
2 miles. 2 miles.
Or half a mile, right? So Grand Canyon is about a half mile deep in some places. Pretty deep. Your sister runs 800 meters, right? But does she race? No, she races. Right. How are we doing? Make sure you have your, at least set it up. So you can get it set up. Do a little bit more than just chilling. So you can chill as long as you're writing. You can write in a chilling way. 122.
So no, that was hilarious, bro. You know that was funny. You like you and that? Isaac, you know that one song by Trippie Redd? By who? Trippie Redd. When he's like, you gonna die, and all that other stuff. You ever heard of that? I'm not singing it. I'm not singing that. I'm not singing it.
Yeah.
Yeah. Wait, what is it? Singing class.
All right, so how we doing? Okay.
We're talking, we're just getting down to a little speed.
Yeah. Yeah, just do the pass.
See?
You okay, Isaac?
Yeah.
All right.
I did that. So, this is helping. You think I can make this?
No, it's probably not a good idea. But, so how many hours is in 143 seconds? Yeah. 0.039? I'll take either way. Okay? So then, okay, so then what do we get for this velocity here in miles per second? 0.0105? Well, let's say 0.011. And then miles per hour? Is that right? No. Oh, I'm sorry. All right, DJ, have a seat. And then how many miles per hour? So about 38.4 miles per hour. Okay? All right, everybody got that? How to do that? Okay, let's go down here and solve these problems together. Okay, so we have the first one is the example of the cheetah. Right, cheetah's fastest land animal, and that's solved in 112 meters, a little bit better than 100 meters, in 4 seconds. How fast do the fastest humans do 100 meters? In 100 meters? About 10 seconds, a little less than 10 seconds. So, she's pretty fast. Even Usain Bolt is like 9.6, I think, 9.7. Still quite a bit off. Cheetah would certainly win that race. Now, okay, so take about 5 minutes and do 2 through 5 here. And then we'll go over these together. And if you can do these, then you should be in good shape for your homework. And if you're watching the video, we'll be back in a few minutes with the answers.